This video is on lattice energy. Lattice energy is a change in energy that takes place when separated gaseous ions are packed together to form an ionic solid. It is also considered the energy released when an ionic solid forms from its ions. It's important to note that these ions have to be gaseous, and we'll see why that matters in a couple minutes. So this is saying that I have some metal cation is reacting with some nonmetal anion in their gas forms to make my solid ionic compound with a metal and a nonmetal. Lattice energy is the driving force behind the formation of ionic solids. It is very favorable in terms of energy. However, lattice energy is not the only energy process involved. So when making an ionic compound, as you learned about before, it's just a transfer of an electrons, but it's not as simple as just taking this electron here and popping it over to fluorine. There's more parts involved with it that we're going to go over. So let's look at this formation of lithium fluoride a little closer. Well, the lattice energy that we're trying to find is going from lithium ion gas plus fluoride ion gas to make lithium fluoride the solid. Well, to do that, I'm starting with the elemental forms of each. So lithium being a solid and fluorine being a diatomic, and fluorine as a diatomic is a gas. So I first need to turn my lithium, my metal, from a solid to a gas, and that's the sublimation of lithium. This has a formation, a heat of formation or heat of sublimation of 161 kilojoules per mole. And that's something we could look up. Then, from having my lithium gas, I then have to ionize my lithium, so turn it into an ion. So I look up the ionization energy, my first one of lithium, making it go from lithium to lithium plus 1, and I give off my electron. And to do that, that requires 520 kilojoules per mole. Okay, so now I've got my lithium the way I want it as the ion. Now I need to work on my fluorine to make my fluoride ion. Well, fluorine I know comes as a diatomic, so I first need to break apart the diatomic bond. So I need to dissociate my fluorine molecule by going from F2 to F. But when this is balanced, I have two fluorines. And I don't want two fluorines, I want one fluorine. So I have to take half of that reaction. So I have half F2 gas to F gas. And so the bond energy from fluorine diatomic to just one fluorine by itself is 154 kilojoules. But I'm doing half a reaction, just taking half of it, so I'm going to multiply that by 0.5. So that gives me my 77 kilojoules per mole. Now that I have fluorine by itself, just one atom of it in the gaseous form, now I can turn it into an ion. Fluorine becomes fluoride, the negative ion, and I do that by adding an electron to it, and that's looking at its electron affinity. So the electron affinity of fluorine, we find out, is negative 328 kilojoules per mole. So electron affinity is binding an electron to the fluorine in its gaseous form to make the fluoride ion. So now I have my fluoride ion and I have my lithium ion, two things that I want. And now I'm going to look at the lattice energy that's putting these two together to make my solid. So I take my lithium ion, the gaseous form, my fluoride ion, the gaseous form, to make my lithium fluoride solid, and my lattice energy is negative 1047 kilojoules per mole. So those are all of my parts. Lattice energy is just that final piece of putting the two ions together to make the solid. So I add them all up, and I cross off the things that match. So lithium gas cancels out with my lithium gas. My lithium ion here cancels out with my lithium ion here. My one electron here cancels out with my one electron here. And I'm left with my lithium solid, which is what I want, my lithium solid, which is here. Then looking at my fluorine, this was my manipulated equation, so I look here. I have my fluorine gas, can cross off with this fluorine gas. My fluoride ion here can cross off with this fluoride ion here. And I'm left with my half F2 gas, my half diatomic fluorine, which I write here. So my true reaction is lithium solid reacts with half a mole of fluorine gas to make lithium fluoride solid. That means that I'm going to add up all of my energies. So my 161, my 520, my 77, because remember I just wanted half, my negative 328, and my negative 1047 to get a total heat of formation for my lithium fluoride to be negative 617 kilojoules per mole. So it's important to note that lattice energy is the driving force. I can come up with the lattice energy by taking a proportionality constant, which has to do with the structure of the solid and electron configuration, times, and we'll notice that we have Coulomb's law here again, my two different charges of my ions, and then divided by the radius of my ions. Now, if we're looking at two different compounds and we want to compare the relative lattice energy between them, we really need to compare their relative sizes, so the radius of the different ions, and the charges of the two different ions. So if my radius is really small compared to another one, because radius is in the bottom, but with a smaller radius we'll have a higher lattice energy. And conversely, if I have large charges are going to give me a higher lattice energy. So you can compare different molecules using that. So let's look closer at two more examples of isoelectronic ions. An isoelectronic ion are ions with the same number of electrons. So if I look at magnesium and oxygen becoming magnesium oxide, I want to figure out, well, how did they become those different ions? Well, magnesium gas first, so if I started with magnesium gas, otherwise if I start with solid magnesium, I have to first sublime it. But I'm saying I'm starting with the magnesium gas, and I need to first get through the first ionization energy. And my first ionization energy of magnesium is 735 kilojoules. I want Mg plus 2, so I have to go through a second ionization of magnesium. And that ionization energy is 1,445 kilojoules. Now we can look at oxygen. Oxygen, going from oxygen gas, we've already dissociated my oxygen molecule, and I'm adding an electron to it because it needs to have a negative charge. I'm adding an electron to it to get O minus, and that has an electron affinity of negative 141 kilojoules, electron affinity, because I'm adding an electron. This is negative 1, but I need negative 2, so this is going to happen again. Plus an electron is O minus 2 gas. That has an electron affinity of 878 kilojoules. So, since the second step of each of these two reactions are very endothermic, why doesn't magnesium oxide just form for magnesium plus 1 and magnesium minus 1 instead of magnesium plus 2 and oxygen minus 2? Well, it has to do with this ionization energy of the second step here and the electron affinity of the second step here. If I compare the lattice energy for magnesium plus 2 and oxygen minus 1, oxygen minus 2, when I add these two up, I get a lattice energy of negative 3,925 kilojoules, as opposed to the lattice energy of my Mg plus 1 and oxygen minus 1. That's the 735 minus the 141. Is 594 kilojoules. So because I get a much bigger lattice energy payout by going with my plus 2 and my minus 2 ions, my atoms are going to like this orientation better because of the larger payout in lattice energy. So that's going to result in a more stable compound. Also, if we compare the lattice energies looking at just relative sizes, we can look at the difference in lattice energies between magnesium oxide and lithium fluoride from before. Well, magnesium oxide, magnesium has the +2 and oxygen has the -2. So just looking at their charges, magnesium oxide has a larger charge difference of -4 compared to lithium fluoride has a charge difference of -1. So here again, a higher lattice energy is going to come out of my magnesium oxide versus my lithium fluoride. So another question comes up, if there's so much to be gained from doubly charged ions, why doesn't sodium and fluorine do this instead? Well, the lattice energy would be greater, however, it's not worth the extra cost of removing a core electron. When we remove a core electron, we've talked about in the last unit how that requires a lot of energy and that really disrupts the electron positions in the atoms, and so that's not worth it to the atom. That's not worth it to the atom to happen. So it just goes to this -1 or +1 charge.